Hello, so today we will continue with chapter 4, which is about phonons and crystal vibrations. Okay, so last time we talked about the system when I have a lattice with monoatomic bases. Today we will continue working on the same system. If you remember from last time, we discussed the fact that in the first two chapters, we were considering a crystal with atoms that do not move at all. And we agreed that this is only the case when we are at zero temperature. However, if we allow a little bit of heat energy or mechanical energy, the atoms will start moving, okay? The hotter a solid is, the more the atoms will vibrate about their positions in the lattice. If an atom is considered individually, its motion about its own lattice point is approximately as the same as that of a simple harmonic motion. However, atoms cannot vibrate independently of each other because they are connected together by bonds. So any vibration in one atom gets passed to its neighbors, which in turn pass the vibration on to their neighbors and so on, producing a vibratory wave that passes through the solid. One way, we agreed that one way of thinking about the atoms in a crystal is as a collection of balls, okay, as a collection of balls. So we see here in the first row, this is if every atom is fixed, okay? If we think of them as balls linked by springs, where the balls represent the atoms and the springs represent the bonds, then if for two balls to be moved further apart and then allowed to bounce back together again in a horizontal direction. This is what occurs when a particular area of a crystal is heated. The expansion in the heated region, so for example, so if I allow some heating, for example, here, what will happen? The expansion of the heated area causes the atoms to move further apart, then they move back together again as they cool. As a result of this motion, a longitudinal wave is created that travels through the solid. The movement is passed from one neighbor to another, as we see here. This will affect the movement of this atom, this will affect the movement of this atom, this will affect the movement of this atom, okay? These longitudinal waves are actually sound waves. Not that we can hear them, no, they are sound waves because sound waves are longitudinal vibrational waves, that is, vibrational waves moving along the same direction as the vibration making up the wave, okay? And we agreed that if we apply Newton's second law, we will get that C into US plus 1 plus US minus 1 minus 2 US is equal to M d2 US by dt squared, okay? And we found this dispersion relationship when we solved this equation. We found omega as a function of K, where omega is the angular frequency as a function of the wave number. We only looked at this zone, okay? When we studied it last time, we only looked at this zone, okay? And there is a reason for that. It's the zone between minus pi over a and the plus pi over a. And there is a reason for that is because beyond, after this zone, everything will become periodic. So if you look here, this will be back again here, okay? And this will be periodic because this function over here is a periodic function. So we have only plotted the dispersion for minus pi over a to pi over a. The reason for this from the dispersion relation, which is actually periodic, of period 2 pi over a. In fact, this is convenient with what we have learned in chapter 2, a system which is periodic in real space with a periodicity a will be periodic in reciprocal space with periodicity 2 pi over a. In other words, if a system looks the same when x is replaced by x plus a, then in the reciprocal k space, the dispersion will look the same when k is replaced by k plus 2 pi a. So if I stand here, for example, this is minus pi over a plus 2 pi over a. it will take me back here and I will be repeating the same motion. Okay. Now, few things we can take, few properties we can take from the dispersion relation in case of the one-dimensional chain. The first thing, sound waves and the long wavelength regime. What does long wavelength regime means? Long wavelength, so if wavelength is long, implies K is very small. Okay, so if wavelength is very large, because if you remember, K is equal to pi over lambda. Okay, so if lambda is very long, K is very small. Now, if I come to this equation over here, omega is some constant multiplied by sine half Ka. If K is very small, then sine theta, so I don't know if you remember this, but sine theta is equal to theta if theta is around 0. Okay, so if whatever is here inside the sine function is very small, then sine theta will be equal to theta. So what do we get here? So for a recall that a sound wave is a vibration that has a long wavelength compared to the interatomic spacing. In this long wavelength regime, we find the dispersion we just calculated to be linear, because now we will have omega. We will have omega is equal to 2 square root of C over M Ka over 2, because we have used the fact that sine Ka over 2 is Ka over 2, and this will be equal to A square root of C over M K, which gives me V sound times K. Here you have to remember the fact that omega, that V of sound is equal to omega over K, and this is what I got here. I have omega is equal to square root C over M K times A. So it is A square root C over M times K. So omega over K is V of sound, and V of sound is speed of the sound is A square root C over M. Okay. Here again, I'm just showing that as K goes to 0, so close to 0 when we are in this long wavelength region. So this is long wavelength region. Let me try to draw a circle. Yeah, this is a long wavelength region, implies K is very small. We get that omega is dependent on K in a straight line, and this is true until, for example, this value, okay, and then it starts changing its direction. Okay. Now, group velocity and phase velocity. Group velocity is the speed at which a wave packet moves. So it is a V of the group, and this is d omega by dk. Okay, you just memorize this. The phase velocity, the speed at which the individual maxima and minima moves, and this is V of phase, which is omega over k. The two velocities, V sound equal omega over k equal d omega by dk, only if the velocities are linear, okay, because then you get the same value. The group velocity is 0 at the Brillouin zone, okay, and this is what I forgot to mention here. This is here, we call it this area over here, that is between minus pi over a and pi over a. We call it the Brillouin zone. Okay, we have seen, we call it the Brillouin zone. Okay, what happens for d omega by dk at this value and at this value is that it goes to 0, because as you see, it becomes parallel to the x-axis or to the k-axis. So the derivative of it will become 0. So the group velocity, which is d omega by dk, which is the first derivative of omega by k, is 0 at the boundaries of the Brillouin zone. Let's solve one exercise. Show that for long wavelengths, that is 1 omega is when lambda is very big, that is k is very small. The equation m d to us by dt square equal to this. This is the equation we worked with last time. Reduces to the continuum elastic wave equation d to u by dt square equal v square d to u by dx square. So here we will be working with s to be very, 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 very small. So it's as if it's a continuum equation. It's not a function of s. It's not like I have this point here and this point here and this point here and this point here. It's like it's a continuum equation. They are very, 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 very close to each other. Okay, and here forgive me because I cannot draw them in a better way. So if we consider them to be a continuum function, then I can take the derivative of u as a function of x, and here I can use this hint, which is f of x plus a is equal f of x plus a over 1 factorial f prime of x plus a square over 2 factorial f double prime of x, etc. Okay, so let's go and see the solution. So here we will use that us is u of x and t, so it is a continuum function of x and t. us plus 1 is a continuum function, it is u of x plus a and t, and us minus 1 is u x minus a t. Now we will use the fact that us plus 1 is us plus a over 1 factorial del u by del x plus a square over 2 factorial del 2u by del x square, etc. And us minus 1 will give me us minus a over 1 factorial del u by del x plus a square over 2 factorial del 2u by del x square. And now if we come to this equation, m d to u by dt square is equal to c into us plus 1, right? So it is us plus 1 plus us minus 1 minus 2 us. Okay, so what is us plus 1? It is us plus a1 over 1 factorial plus del u by del x plus a square over 2 factorial del 2u by del x square. And from the second term, I will just write it down, minus 2us. Minus 2us cancels out with us and us here and here. Okay, here I have minus plus a del u by del x. Here I have minus a del u by del x. And what I will be left with, c a square over 2. First of all, a square del 2u by del x square over 2 plus a square over 2 del u by del x square. This gives me a square del 2u by del x square. So I have ca square del 2u by del x square. If I take m to the other side, it will become del 2u by del t square is ca square over m del 2u over del x square, and this is nothing but b square. So I have proved what the question is asking me to prove. So I will stop here because this is a continuation for what we discussed last time. That is, if I have a lattice with monatomic bases. Next week, we will be discussing the case when we have a diatomic basis. Okay, so instead of 1 atom per basis, we will take 2 atoms per basis and see how the equations will look like. So that's it for today. Bye-bye.